Okay, good afternoon. Let's start our lecture. So let's continue on the line equation here. This is just a quick review. In previous lecture, we basically try to derive an equation for a line in 3D space. So here's a line in 3D space. So how can we describe this straight line here in 3D space, right? We basically, the objective we did is we used a so-called parametric equation to come up with a parametric equation to describe the trajectory or to describe this line in here. So ultimately, what we find is, if we have a line which is parallel to a vector v, for example. So basically, we call the v at here, we call it parallel vector. So parallel vector to the line L. At the same time, if we also know that the line goes through a certain point P, so let's call it P naught. So this P naught, suppose that it has a coordinates x naught, y naught, z naught. This is the point on the line. And that will be enough for us to come up with a so-called parametric equation for this line at here. So parametric equation for line L, it can be described as x equal to x naught plus k times v1, and y equal to y naught plus k times v2, and z equal to z naught plus k times v3. So this is basically so-called parametric equation. And here, the k at here is a parameter, right? So this is how it's defined. This is a parameter here. In everything x and y, z are in terms of the parameter k. So you can choose a different parameter, right? You can choose t, as we did in our derivations. So that's fine, okay? And we actually will look at basically different meanings for the parametric equation. If you just look at purely mathematic equation, so here it is, that's purely mathematic, right? It doesn't necessarily have to tell you any physical characteristics or anything like that. So you need a parallel vector, you need a point, and then you can form the parametric equation for the straight line L. So that's just as simple as that. Is that good? Yeah. So basically, if at this stage, if you recall how it's derived, that's fine. If you forgot, then at this stage, at least what you can do now is, this is a formula for a straight line equation in a 3D space. And how would you be able to form this straight line equation? You need a point on the line, and you need a parallel vector v at here that is parallel to the line here. So v here, this is v1, v2, v3. Yeah. Then I can use the two information at here to form this parametric equation for the line L. So just as simple as that. Then the x, y, z at here, what do they represent? This basically represent it's the coordinates for a point, any point on the line L at here. So if you substitute the k with the different values, if you substitute 1 or 2 or 0 or 0.5, or 0, then you will get a coordinates at here, and that coordinates basically represent it's a point on this line L. Is that clear? Okay, so that's basically what happens here. So now you think about it. A lot of we're going to have some exercise. So just like when we learn planes, right? There are always two directions when the question is given. One direction is giving some information and ask you to derive a line equation. That's one type of question, right? And then the other type of question is give you a line equation and then ask you to do something else. Okay, so if it's the first type of question, give you a line equation, ask you to do something else. Sorry. The first type of question, give you some information and ask you to derive the line equation. Then what do you need to do? You need to try your best to find a point on the line, and you need to try your best to find a vector parallel to the line. If you can find these two, then you can form the line equation using this formula. Does that make sense? Right? And the other direction, if you're given a line equation and asked you to do some other type of tasks, then the first step you can do is, before you start to do anything else, the first step you can do is what? You can immediately write down a point on the line, and you can immediately write down a parallel vector to the line. Okay? Yeah. So that's the idea here. So let's see, for example, right? Let's see. Give you a very simple example here. If I give you a line equation, x equal to 3 times k times 2, and let's say use 2 times k at here, and y equal to 4 equal to 3 times k, and z equal to 5, 3, 4k here. So for example, this is a line in here, right? This is a line. So the first step you can do is you can extract the point on the line, which is 3, 4, 5. Okay, that's quite easy to get. Okay, or it's equivalent to setting k to 0, then you get 3, 4, 5. This is the coordinates, right, on the line here. And then you can get a parallel vector, okay, to the line. And the parallel vector here is 2, 3, 4. Okay. So that's something that you can immediately write it down before you proceed for that question in here. But you also has to be aware, has to be clear, is this is the point that you choose or you use for on the line here. But how many points do you have on the line? Infinite, right? So if you set k to different values, then you get an infinite number of points on the line. So if you choose the different one, absolutely fine. And then this is a parallel vector, 2, 3, 4 for the line in here you choose. But you also need to be aware is there are infinite parallel vectors to the line. If you multiply 2, 3, 4 with a scale, with any scale, any values, right? And that's still a parallel vector to the line. Does that make sense? Right? So you just have to be aware that there are infinite number of solutions, right? So there are infinite solutions for a line in 3D. Okay. Yeah. So just don't be surprised if you see, oh, these two actually looks different, but they actually properly described is the same straight line in the 3D space. So that's just something you just have to be aware of here. Okay. Okay, so let's go over a few examples just purely on lines that are here. Okay. I'll give you 2 points. So give you 2 points and find the line that go through these 2 points. Okay, so here's basically the first type of question I was talking about. So give you some information and asking you to find the line equation. Okay. So the logical procedure set here is just stick to what I said. Okay, so then if you're required to find the line equation, then you just have to try to find a point on the line and a what? Parallel vector. Okay, yeah. So in this case, you already got 2 points. So the first part is done, right? So you just need to find a parallel vector to the line. Okay, so you just need to find a parallel vector to the line. So what will be a parallel vector to the line? PQ. Yeah, exactly, right? So PQ will be a candidate here for parallel vector. So let's say I call the V here equal to PQ. So you calculate QQ, this minus that. So that will be the parallel vector to the line here. Okay. And then you can write down the line equation now. So this is where you probably end up with a different answer. If you choose point P for your equation to form the equation, so if I choose point P, then -3 plus this is -4, right? -4 minus 4 times, let's say I use a different parameter called, let's see, in this time I use a t, and then y would equal to 2 minus 3t, and z equal to -3 plus 7t. So that's the parametric equation for the line if I choose this point P, right? If you choose point Q, and you end up with a different equation for this part at here. Sorry, yeah. A mistake. PQ. 1. Oh yeah, this is positive, right? Yeah. Good. -1 minus 2, -3. Yeah. Good. At least where somebody's awake. So if you choose Q, right, so you can write it down yourself, and you'll get a different set of equation. But bear in mind, they are actually describing the same straight line here, right? Yeah. Okay. So that's that. So let's take a look at another one here. So this is a very typical question you probably will see in an exam, in a midterm type of exam. Okay. Yeah. So we'll give you a point 115, and we'll also have a line given. So the line at here is x equal to 1 plus t, y equal to 3 minus t, z equal to 2t. So giving a point and giving a line. So here's a point, here's a line. Okay, so as illustration. Okay. So what do we need? We want to find the shortest distance from the point S to the line L. So find shortest distance from this point S to the line L. As a matter of fact, I think we had a similar question. We learned plane. We said find the short distance from point to a plane, right? Yeah. So this will be a short distance from the point S to L. And there are actually really a lot of different methods. I'll show you really several different ones here. But before we start, let's just examine this question again here. Okay. But before we proceed here, actually, it's also good to establish some sort of a common sense or some sort of pre-knowledge before you proceed here. So you're asked to find the shortest distance from this point S to the line L. But the first question you might actually ask is this point S on the line or not? Right. If the point S is on the line, then short distance 0, right? Yeah. So that's probably the first thing you can double check. But of course, you probably don't have to, because if the question really asks you, then the S is most probably is not going to be on the L, right? Yeah. But it's also good to check this whether the point S is on the L or not. Okay. Yeah. So that brings the question here is, how do you know whether a point is on the line equation or not? How would you check? Right. How would you check whether this point is actually on this line in here? What's your thought? Yeah. Go ahead. Yeah. Did you raise your hand? Yeah. check your line equation, and then what? Okay, that's good. So how do you check? How do you compare or check? This is 0.130. Okay, it's different from 115. You think? That's different, but that doesn't validate that that point is on the line or not, right? Yeah.
So you should be able to find a plane equation where the point and the line lie on the.
I should be able to find a. Okay, you're actually making it more sophisticated now. You only have to find a plane here. Yes, you can find a plane that passing through this line and the point, but the point here is we're trying to verify whether the point is on the line or not, right? Okay, the one in the back who raised your hand, yeah. Yeah. Exactly. Yeah. So what's your name again? Isaiah. Yeah. So what he mentioned that the method is plugging the coordinate for the s into this line equation and then verify, right? So that's how you can. Basically, what he was trying to say is, if the s is on the line equation, that means there got to be a t value, right? When you start the t value here, 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 then I'll give you the coordinates 115. Does that make sense? So we just had to find whether the t value exists or not. If it doesn't exist, then the point s is not on the line. If it exists, then it's on the line, right? So that's the point here. Okay. So let's try this first. Okay. So this is a very fundamental skill. Okay. A lot of times you are actually trying to verify whether the point is on line or not, or try to get a solution between two lines, or try to get an intersection between the line and the plane. So that's the sort of a fundamental skill. Okay. So I'm going to substitute the coordinates into the line equation here, and then what we're trying to do is we're trying to find whether a solution exists or not for the t value. So let's say, for example, I'm going to let 1, right, equal to 1 plus t. So what does that give us t value? T equal to 0, right? So that's based on the x coordinates. You need a t equal to 0 to get 1 at here. And then if I let another one here, the y of t equal to 1 and equal to 3 minus t, we end up the value for the t would be 2, right? So obviously you don't have to proceed anymore. You need a two different t value in order to get the x, y coordinates. So that basically tells you s is not on the line. Okay? Yeah. Okay, if s is not on the line, then there exists a shorter distance from this point s to the L. Okay? Yeah. So now we just need to proceed and then see how we can do to find this shorter distance. Let's call it d at here. Shorter distance basically means you draw a perpendicular line from S to the L, and that distance will be the shorter distance. Okay. There are many different methods actually. At least I can give you at here four different ones. Okay. So before I jump into it, okay, and I want you to basically think back what we learned, okay, from previous lecture, including the 2 reviews on the vector concepts, okay, yeah, and think about if you can come up with a sort of you don't have to solve it, but just think about a direction that you think you can work on to solve this question right here, okay, yeah, just a direction, okay, yeah. I'll give you 1 or 2 minutes to think about it, okay. If you can think of something, and raise your hand, let me know, okay. Oh, that was already here.
Use the point on the line that you have,
okay,
and the point S. Make a vector between the two. Figure out the parallel to that vector that would be laying on the line, and then from there you can figure out your perpendicular, which is the shortest line.
Excellent. Sir, what's your name again?
Nathan.
Nathan. So what Nathan was saying is, find a point on the line. Well, that's good, right? 130 is a point on the line. So let's say call this is P here. So that's 130 That's a point on the line here. That's actually the first step. I guess I mentioned that you probably want to write it down right away, right? So that's a point on the line, and parallel vector is 1, -1, 2. Okay. So then he suggested is let's create a vector from P to S, okay? And then we try to find the parallel vector of the PS, I guess in this direction and here, right? And then we can find the perpendicular one here, okay, whose distance is basically the shorter distance. Okay, that's absolutely right. Good, right? That's one way of doing it. Okay. Of course, now down to the detail. Down to the basic detail is how do I find this PS parallel? If you recall that in the review section, we reviewed the concept vector. One part is using dot products. It's the projection, right, of one vector in another direction, and you can get a parallel vector. So that's one way of doing it. Excellent. So let's work on this, and then there are many. There's a few others. And I want you to think about it while we let's just solve based on the first methods here. Okay. And you can still think of ways if you can think of. Okay. So first step, find the P, create a PS vector. Okay. So then PS vector at here. Okay. So that's 115 minus 130, and we get. Sorry, I should use a bracket here. Well. Really, I should. Sorry, it's proper rewriting it. Okay, proper rewriting it. So that's 1, okay, minus 1, and then 1 minus 3, and 5 minus 0. So get 0, -2, 5. Okay, so that's your PS vector at here. Okay, so get the PX vector, and then we try to get the parallel vector PS in the direction of the parallel vector V. Okay, so PS parallel. So if you recall, this is basically the same thing that we did in the review section. If you are trying to find this PS parallel, vector always have two components. One is the length, the other is the direction, right? So the length at here is the PS. How do you get the length again? When you try to get the length, the projected length, you use the vector dot what? Not the parallel vector, dot the unit vector, right, in the parallel vector direction. So let's see, I use a V hat at here, okay, for the dot product, and then time the direction and V hat. So of course, what's V hat? V hat is a normalized V. So that's your V hat. And V already derived right away here from the given line equation, which is 1, -1, 2, okay, divided by its direction, the length, okay, which is √6. So that's your V hat. Now you plug everything into here. So you got everything now. You vector PS, so you have it. You have V unit vector. So plug everything into it, and you will be able to get this parallel vector turn out to be 2, -2, 4. Okay. So that's your parallel vector. And then we can get the perpendicular decomposition component. So the perpendicular one is the PS minus the PS parallel. Right. So this perpendicular one is PS minus the PS parallel. Right. So that'll give us this -2, 0, 1. So finally, you can calculate the distance by calculating the absolute value, okay, the length of the PS perpendicular. So you end up with a √5. Okay, so that's the first method. Okay, first method. Good. So in this method right here, we basically what we use is a sort of a dot product concept, right? Yeah. So let's see another method here. Let's see if anybody can come up with another method here. So this is S right here. Okay. Okay, so here's the same question. So let's see, anybody, yeah?
What a point right under the vector.
You mean this point?
Yeah, like right there.
Okay, so let's call it Q at here.
You know that the line has an infinite point, so make the point equal the line equation.
Ah.
So like 1 plus t, 3 minus t.
Okay, so line is, what's the line again? It's, line equation is 1 plus t, 3 minus t, 2t, right? Okay, so you have 1 minus t, 3 minus t, and 2t. Okay? And then what? What do you want to do?
Make that equal to x plus t for the point under t.
Okay, so you're letting, okay, good. So you let basically the q. So I don't know what the q is, right? So let's see, we pick a q, x, y, z. Is that okay? Maybe let's see, how do we make it a little more? So let's make it the q at here, x, y, z. So q is on the line. So basically, this is the coordinates, the q at here, right? Okay. So then what next? Keep going.
We make a vector between q and s.
Okay, so you create a qs vector here, and then what?
You do the scalar, you need the t, so we have to make a scalar value between qs and the line of the vector, which we have.
You make a
Dot product
dot product with what?
with the parallel vector.
Okay, with a v, and that should equal to?
0 because it's perpendicular to the qs.
Very good. Yeah. Okay. Very good. What's your name?
Derek.
Derek. Yeah. So Derek suggested idea. You know, this is actually one of the methods I'm presenting at here too. You're looking for the shorter distance, which means you're looking for what? Alternatively, you're looking for a point Q such that the SQ is perpendicular to the L. Okay. So if you can find the coordinates for the Q, then you can find the shorter distance by getting the lengths between S and Q, right? So that's the idea. But we don't know what the Q is. What we do know is the Q is on the line L here, right? So that's the basic we know. So what's the line L equation? This is a line L equation. So basically any point on the line L has this property, right? So Q has these coordinates. So basically the Q has a coordinate 1 minus t, 3 minus t, 2t. So at this stage, right, at this stage the Q is nothing special. It's just a point on the line, right? This is just a point on the line here. Okay. So nothing special, just a point on the line. Then we can create a vector between Q and S using this general coordinates for the Q. We have S already, so we can create the QS right here, and that gives us basically use the coordinate of S minus the coordinates of Q. What's the coordinate of S again? It's 115. Okay, so it's y minus t, y minus 3 minus t, and then 5 minus 2t. Right. So that's the QS coordinates. So then you get t here. Negative 2 plus t, and 5 minus 2t. So that's the QS vector. Okay. Still, nothing special. It's just a Q on the point on the line here, and then you create a vector between Q and S, right? A general Q. And then come to the special part now, because you are looking for what you're looking for is a special Q point, which give you a perpendicular relationship between this QS and this line L. And we also already have the parallel vector V. So that means what we want is, right, we want the QS to be perpendicular to the V at here. So that's what we want. Okay. And when you see two vectors are perpendicular, basically means the two vectors dot product equal to 0. Okay? Yeah. So now things are putting things together, right? So dot product is the 0. I already have the QS vector here, and then I have the V vector here. So then you put the dot product. So what does this dot product give us? So this one here is a T. Did I make a mistake? What's the line equation again? Oh, so the line equation 1 plus T, right? The line equation is 1 plus T. So it's 1 plus T here. So this should be negative here. Is that okay? Yeah. So, and now I can proceed at here. So negative T at here, negative 2 plus T at here, 5 minus 2T dot the V, and V at here is 1, negative 1, negative 1, 2, right? Yeah, 1, negative 1, 2. That equal to 0. Okay. Carry out the dot product calculation. You get 12 minus 6T equal to 0. You end up with T equal to 2. Okay. So basically, when T value equal to 2, your Q, right? So when T equal to 2, what is the Q's coordinates? The coordinates here you get which is 3, 1, 4. Okay. So that's your Q coordinates. Or you can just simply, what is the QS vector? Substitute T over here equal to 2, negative 2, 0, 5 minus 2, 4, 1. So negative 2, 0, 1. That's the QS vector. Then your shorter distance is absolute value, or the norm, the length of the vector, same as before, at root 5. Okay. Okay? Okay? Very good. So, okay, so I think this second one here, somehow still using dot product here, right? Can you think of another perspective using the cross product? How would you be able to make use of cross product to come up with the answer for this one here? So let me draw this again here. S. Okay. Is there any way you can use a cross product to come with a solution? Anybody? What's cross product? Let's say when you write a cross product, A cross B equal to what? A, B, sine theta, and then there's a direction here, right? But in terms of the length of the cross product, this is the length, right? This is the length of the cross product. Okay. How can we relate this question to this cross product formula and here? So we're looking for which one? We're looking for this, right? Okay. So if I label this as a theta, okay, I'll label this as theta here. Would that make it easier to find a solution at here now? So this is what I would do. I'll try it out. So let's, yes, go ahead.
So we can find theta from the cross product.
Uh-huh.
And we have length equal to S.
Times.
And we can use trigonometry.
Yes. Right. Very good. Okay. What's your name again?
Netic.
Netic, right? So that's good. So if you can find a theta, then you can just choose PS times sine theta. You get the D here, right? Yeah. What's even better, you don't have to find a theta. Look at the formula here. What's this formula? PS cross V equal to what? PS V times what? Sine theta, right? So PS times V times sine theta. And I'll rearrange this slightly here. Okay, so move the sine theta a little bit forward. And what is this term here? PS sine theta is what? This is a D. That's exactly what we're looking for. So D at here. Okay. So now you solve for the D here. You see your D equal to what? There we go, right? That's how you can calculate this shorter distance D now, right? Shorter distance D. So let's do a little bit of calculation. If you recall that, first you need to calculate the cross product. And to calculate the cross product, you do have a formula if you remember. And the formula is basically to get the determinant for a 3×3 matrix. IJK is the first row. Second row here is your PS vector. Third row here is your V vector. Calculate the determinant of 3×3. You do have a formula, but you can practice a little bit. You'll get that. So which you get I hat phi plus phi j hat plus 2 k hat. So PS cross V, you get this vector. And then in terms of the calculation of the D, you need to calculate it here is the you need to calculate is the length, right? So this basically means it's the length of this PS vector. So the D here, you get the length, so 1 plus 25 plus 4. Bottom here, you get the length of the V. Length of the V is root 5, okay? Root 6. Okay. So 1 plus 1 plus 4, so root 6. So altogether, so 25 plus 4, 29 plus 1, 30. So root 30 over root 6. Again, you get the root 5. Okay. So that's another way. This is a cross product here, right? Cross product. Okay? Yeah. Any questions so far on this cross product here? Okay. Now, even better, I want you actually to look at this results today here. D equal to PS cross V over the V. And I want you actually to relate to one of the things that we learned in the review section. If you recall that, when we learn review here, we have, for example, if we have 2 vectors, okay? What is the area of the parallelogram formed by the 2 vectors? Do you remember that? Area equal to what? Cross product, which is this, right? Yeah. So the norm or the length of the cross product, that's the area of the parallelogram, right? Okay. But in terms of the basic geometry, how would you calculate the area of the parallelogram again? The area equal to what? Equal to the base length times the height, right? Times height. So the area equal to the base length times height. Okay? Yeah. So now you see, if I know the area, I can solve for the height, isn't it? So the height equal to what? To the area of the parallelogram divided by the length of the base of the bottom. And the bottom here is this. If you look at the results here compared to that, you see that that's exactly the same thing, isn't it? Right? Exactly the same thing. So you have your PS here, you have the V at here. So you can form basically, here's your P, here's your PS. Okay, so this is your PS vector, and then this is your V vector at the bottom here. And you can form basically a parallelogram and then you try to find it here is the shorter distance. Does that make sense? Yeah. So that's another perspective, right? So you're, either way you get the same answer, but there's so many different perspectives that you can actually try to get an answer here. Okay. Yes.
Sorry, for the last one, how did you find the length for vector v? You explain for the last method.
This one?
No, above.
Oh, above. How did I find the length of v? You mean?
Yeah.
Oh, well, you just have to. Your v is already given, right? Your v is given. Your v is the parallel vector, which is 1, -1, 2. So the length is just square root of 1 plus 1 -1 squared plus 2 squared, which is square root of 6. Okay, is that clear? So I want you to basically, not just think about it. There's only one solution. As a matter of fact, there's another one. So I'm gonna skip that. You can take a look at the lecture notes. There's another method here, also possibly can solve this question in here. And this method is relatively more complicated than the other three methods presented here. Okay, it actually use both cross product and dot product in the fourth method. Okay. So take a look at the lecture notes as to the fourth method here. Yeah. Okay, so I think I know you asked a question before we finish this question here. I think one of the students actually, when I soliciting for answers, one of the students actually suggested to find the plane going through this line L and the point S set here, right? So okay, that's a very legitimate question. You could actually see that kind of question here. So now let's try to look at this. Find the plane going through L and this S set here. What will be a plane going through the L and S? So we're sort of relating what we learned for plane and learn for the line and here together. Okay. And then first thing that you probably should actually be very certain is when you're presented with the L and the point that is not on L, then you will be able to find a unique plane, right, passing through this L and this point. Okay, so you're not going to find another plane or two different planes or three different planes satisfy the same condition. Okay. So, and even before you proceed, just think about the directions that you should go, right? So now you're asking to find a plane equation. So now tell me, basically, you can think about it together. What information do you need in order to create a plane equation? Number one, you need a what? Point plane. Number two, normal vector. Okay. So you need a plane. You're trying to find a plane passing through this one here. So now naturally you already got a point on the plane here, right? Yeah. So now all you need is to find a normal vector now. Okay. Yeah. So how can we create this normal vector based on the given conditions in here? Yes.
The V crossed with the PS.
Very good. Yeah. So as usual, you can draw the PS and the V at here, and you got two vectors at here. Then you can use the cross product from V to PS or PS to V, and you get this normal vector. Okay. Excellent. Yeah.
Doesn't matter which way you go.
Doesn't matter. Yeah. So normal vector could be either this way or that way, right? Yeah. So V cross PS is probably give you a number, and then PS cross V is the negative of that number. Yeah. Good. So it won't change your plane equation, okay? If you wonder about that. So let's do this cross product. We actually did the cross product in one of the methods here, right? In this method here, we did the cross product here. So you should be able to have that answer. So that gives us 1, 5, 2. So I use this cross product results and the point S to find the plane equation. So now back to the plane equation formula. So x minus the point, and S is the point. So S is 1, -1. Sorry, what is S again? Is 1, 1. What's S again? Sure. 115. So S is 115 right here. So now x minus 1 plus 5 times y minus 1 plus 2 times z minus 5 and equal to 0. So, right. Now you don't have to. This is basically substituting in the formula, right, for plane equations. So the coefficients that are here, if you really see, this is 1, 5, 2. So that's your n. This is your point, 1, 1, 5. Okay. So you can stop here, or you can simplify it a little bit further, which is also okay. So that will be the plane equation here. Okay. So it's a unique plane, and it's uniquely determined by the line L and this point S. Okay. So essentially, any sort of future questions, it's all about applications of dot product, cross product. So all the different things mixed together to try to find an answer here, right? Yeah. Any questions so far on this question here? Okay, so a very typical question. That's why I'm spending relatively a little more time on this kind of question here. Okay, so let's look at another example. But in this example, it's a very different perspective. Okay, this is actually not really for you to solve a specific line equation or a plane equation. It's more just for you to gain a better insight into this line equation here. Okay, for this equation. So you all watch Jerry and what's the mouse name again? Tom cartoons, right? And Jerry is always the one trying to catch this mouse, the Tom. Okay. So let's say in a very unideal situation, the Jerry is traveling on a straight line. Okay. And then the mouse, okay, is also traveling, okay, on a straight line here. Okay, so so far, okay, what I give you, okay, it's a pure mathematical equation here. So the two parametric equation. So we're looking at a simpler case. It's 2D. That's why you don't see the z right at here. So z equal to 0. Okay. So this is a pure math equation. So saying cat is traveling on the line and mouse is traveling on the line here. Okay. So let's give it thinking in two different directions. One is completely mass perspective, and the other is more or less in physics or a time history trajectory, that type of idea. Okay, perspective. Okay. So first of all, let's think about in terms of time history here. If this is a cat equation in here, right? So the cat's equation. This is where the cat is traveling here, and if you recall that, okay, when we derive the line equation, the first method used is to use the velocity idea to derive the line equation. So if I look at this cat equation here, what's the parallel vector? Parallel vector is what? 2, -3, 0, right? Okay, that's parallel vector. What's the mouse parallel vector? 0. Good. Okay. So that's the math idea, parallel vector. But if I translate to the velocity idea, so I can see, let's say this is a cat velocity, and this is the mouse velocity. Okay. Yeah. So I'm saying the cat is traveling at a constant velocity, and here, and the mouse is also traveling at a constant velocity at 140. Okay. So now you think about it. First of all, the v1 and v2, are the parallel vectors? No, right? So okay, so one traveling in one direction, the other traveling in another direction, isn't it? Right? Okay, yeah, because they're not parallel. If they're parallel, then the cat will never catch the mouse, right? Yeah. Okay, so now you established more or less actually a sort of a spatial idea now. So cat is traveling one direction, mouse is traveling one direction. Okay, so there's a definite possibility that the cat could catch this mouse, right? Yeah. But there is also a definite possibility. It's not uncertainty. It's a definite situation at here. So if the cat is traveling in this direction, mouse is traveling in this direction, what happened to the two trajectories? Parallel? No. Intersect, right? The two trajectories must intersect. But the two trajectories must intersect doesn't mean what? The cat will definitely catch this mouse. Does that make sense? Or in other words, the cat doesn't necessarily will meet the mouse at where? At an intersection point. Okay? Yeah. So that you establish the right idea, and then you actually help you immensely in terms of solving this following question here. Okay? So let's put in another perspective here, looking at the equation here. Remember the first column, -4, 7, 1, -6 here. We think of this what? We think this is a what? This is a point on the line, right? So if you let the t equal to 0, let the t equal to 0, this is basically the point when t equal to 0. And when t equal to 0, if I think of as a trajectory idea, basically at time equal to 0, we usually call it what? The initial points, right? The initial position. Okay. So at t equal to 0, the cat is at -4, 7, and the mouse is at 1, -6. Okay. So that's another physical meanings you can give based on the two equations here. Good. Yeah. So here's basically my two questions. Okay, the first part of the two questions here. So the two question is, will the cat catch the mouse? Okay. And the second part of the question will be, if the cat can't catch the mouse, how will the cat do? Okay. Well, what can it do in order to catch the mouse? Okay, that's the second part. But let's deal with the first part first, right? Yeah. So the first question here is basically, will cat catch the mouse? Okay. Yeah. And I need you basically now to try to make use of or differentiate. Okay, the idea I mentioned. One concept is the intersection between the 2 points, the 2 lines, and the other is now you think that there's a moving point on the 2 lines. Whether the 2 points, two moving points, will meet at the same time at the intersection point, right? Yeah. So that's the point here. Okay. Okay. So how can we solve this question in here, right? How can we solve this question? You have 1 or 2 minutes to think about it. Yes. Yeah. Very good. So we equate the x and y at here. So I'm going to equate x with this, equate x with this one here, and equate y, this one with this one here. Okay? Yeah. Very good. So we're going to let the x equal to -4 plus 2t, okay, equal to the other x, which is 1 plus t at here. So solve this one here. We got the t equal to 5. Okay? And then we let the other one here, 7 minus 3t equal to -6 plus 4t. We end up the t equal to 13 over 7. 13 over 7. So now you immediately can see, okay, in order for the first one to be the same, you need t equal to 5. And actually, I'll emphasize a little bit once we finish this one. And then when you let the y equal to each other, you got a t equal to 13 over 7. So these are not the same. So that basically tells you will the cat catch the mouse? No, right? Will not, right? So will not. Okay. But before we move on here, okay, and I want you to understand it here. So if I just look at this first solution here, right? If I just look at the first solution, t equal to 5. What does t equal to 5 actually means? physically, not mathematically. So you start at t equal to 0, right? And then when t equal to 5 seconds, for example, that means that the x for the cat is the same as the x for the mouse, right? Yeah. So that's what this value here means here, right? Okay. Now, before we move on here, now let me ask you here. This basically, what would be the intersection points then? How would you solve for the intersection points? So we understand now when you have a two lines in 2D space, you have 2 lines in 2D space. As long as the 2 lines are not parallel, they definitely will intersect somewhere, right? Okay. So now the question here is, let's say this is the cat and this is the mouse at here. So what will be the intersection point? So what's the coordinates for the intersection points at here? How would you solve for that for this one? Yes. So you're trying to put the 2t value into where? Either the cat or the mouse. See, that's the pitfall here, trying to catch you. This is exactly the point of trying. So if you substitute the t here, fine. Which one would you substitute then, right? Top t for the x, bottom t for the y. But you see, what I just mentioned here, this t here, it's a time. We understand now the t here is a time instant, isn't it, right? This is basically 2 different time instants. You see that, right? Yeah. But does this mean that at this time instant that the cat or the mouse is at the intersection point? We don't know, right? That's not exactly the case here. This is a time instant here. That's not the t value that's supposed to give you this intersection point actually. Maybe at t equal to 5, your cat is here. Maybe at t equal to 13/7, the mouse is over here. That make sense? But that's right. But that doesn't mean that this will be maybe it could be the time moment at the intersection. It could be, right? But we just proved that it's not, because there are 2 different t values for the x and the y. So when you need this much to try for the x to be the same, you need that much for the y to be the same. You can never get the same t value for both x and y. Yes?
Can you express t as function of x and plug it in y and equate it?
Excellent, excellent. Yeah. What's your name?
Oh.
Yeah, Fawzi. See, that's the point here. That's exactly. Now it's a different perspective now. You're talking about the intersection here. So going back to this line equation here, right? Going to the line equation. What we have to do is we have to change our mind back to the mass perspective. Basically, here's a parametric equation. Here's another parametric equation. So I'm going to change the t actually to a different parameter. You can change this to any parameter other than the t here. Just change to a completely 2 sets of a parametric equation. So then you see, okay, a line for the cat. If I just rewrite it here, so x equal to -4 plus 2t, and y equal to 7 minus 3t, and for the mouse, okay, and I'll write it as x equal to 1 plus s, for example, y plus -6 plus 4s here. Okay, yeah. So this is basically, forget about the moving points, right? Forget the moving point. Just think of 2 parametric equations for 2 lines, and then asking for intersection points. Okay, intersection points. So then this time you let -4 plus 2t equal to 1 plus s. The other one, 7 minus 3t equal to -6 plus 4s. So 2 equations, 2 unknowns. Now you can solve for t and s. So you get t equal to 3, and s equal to 1. Okay, so you'll get these numbers here. Okay. So now you can verify. Okay, so I'm going to substitute the 3 back into the cat equation, because the t is for the cat equation, the parameter for cat. And what's the coordinate when t equal to 3? So x equal to -4 plus 6, 2. 7 minus 9, -2. And you substitute s into the mouse equation, 2, -2, so you get the same answer, right? Yeah. So that's where they intersect, positive 2, -2. Okay, that's where they intersect. Good. Okay. So now let's move on to the second part of the question here. So we just proved that the cat will never catch the mouse if we're given the current trajectory and the current type of motion at here. Okay? Yeah, so not going to catch. So then next second part is, how can we change the cat's motion? How can we basically modify this cat equation here? Okay, so tell the Tom, okay, you need to do this and that in order to catch this mouse area here. Okay, so that's the idea. Okay, so let's see. Here is the question in here. Okay, maybe we can ask for is, how can the cat change its speed in order to catch the mouse? Only change the speed without changing the direction. Okay, so same direction without changing the direction and initial point and initial location. Okay. At what speed will the cat catch the mouse? So let's try this one here. Okay, and this will be my approach at here. Okay, yeah. Here's the original speed, velocity. I should say velocity, not speed. At what velocity? Here's the original velocity. That was 2, -3, 0. Okay, this is the original one for cat. Okay, and we want a different one. Okay, we want a different one here. Whether it has to be a little faster or to be slower, we don't know, right? Yeah, but we just want a different speed in order to catch this mouse here. Okay. So how do we formulate this question here now? Basically, right? So we want a different speed. Basically, we want v. Let's see, a new speed here. Okay. We want a different new speed for the cat. So to formulate the question here is, when we're not changing its direction, okay, same direction, okay, then what we can do is we can normalize. Let's see, this is the speed at here. Okay, this is the speed for the original speed, v1 at here. Okay. We can normalize this v1 into a unit vector first. Okay, unit vector, and then use a constant c, okay, time this unit vector. Okay, so let's define this as the new speed or new velocity for the cat. It's okay, right? Because I don't know what the c is. I just want to be a new speed at here, right? It could be faster, could be slower. So we can normalize this v1, and that's quite easy. So 2, -3, 0, and divided by its length, which is 13. Okay, so that'll be the new speed for the cat at here. Good. Yeah. If we could find a proper value for the c, then we'll be able to find a proper value of the c such that the cat can catch the mouse. Right? So that's the idea. Okay. Okay. So I don't know what the c is yet, so I'm going to just keep the c at here. Okay. then with the new speed, we can define basically a new trajectory, new motion for the cat. I will use this new velocity here to write down this updated motion for the cat. Okay, so that's -4, still the same location, right? The same initial location. And here is your parallel vector now. So c times 2/√13 times t, and y equal to 7 minus c3/√13 times t. Okay, so that's the new motion for the cat, right? It's updated. It's just that we don't know how we will update this yet, right? How we will update this. So now back to the original idea, right? Here is the cat's motion. Okay, what does the catch mean? Right? What does the catch mean? What does the catch mean? That means the cat will arrive at this intersection points, right? The same time as the mouse. Okay, the same time as the mouse. So now if you look at this one here, so what we want is, if you look at the previous solution in here, okay, the previous solution. Here, when we calculate this intersection point, here, we have two parametric equation. We let the both sides equal to the same, and we solve for the intersection. We got the t equal to 3, and we solve. We got s equal to 1. That makes sense, right? Okay, yeah. So this is s equal to 1 here, right? It's s equal to 1. Okay. Now, if I change the s back to t, okay, change the perspective again. Change this s back to t here. T, this is not s anymore. This is a t again, right? Then physically, what does that mean? It means the mouse starts at 1, -6, and when t equal to 1 second, and the mouse end up at where? 2, -2, right? 2, -2. Okay, yeah. So basically, the mouse is not changing its motion, right? The mouse is still going as it is. Okay. So physically, what it means is the mouse starts at t equal to 0. When will the mouse end at the intersection? When t equal to 1 second. That make sense? So it takes 1 second for the mouse to reach that intersection. So it also means what? You also need the cat to do what? Exactly, right? You also need the cat to spend only 1 second to end up at the intersection, basically. Okay? So now let's go back to this equation here. So I'll write down here. So mouse takes 1 second to reach intersection. Which point is that? That's 2, -2, right? Okay. And of course, we also need 1 second to reach. We also need the cat to reach the same intersection at the same time, t equal to 1 second. And here is your new updated cat's motion equation at here. See, right? This is your cat motion here. So back translate into the same meaning here. You need this equation here to what? You need the x, y to be at which location? 2, -2. At what time? At t equal to 1. So that's how you can substitute the 2 at here, -4, c 2/√3 at 1 second here. Okay. The same thing. Yeah. And you solve, you get the same c value. You get a c equal to 3/√3. Okay, 3 times √3, √13. Okay. C times √13. Okay. So now I can see the updated velocity for the cat needs to be c times the unit vector, which end up 6, -9, 0 at here. Okay? Yeah. If the cat travels at this updated speed or velocity, then it's guaranteed that the cat will catch the mouse at the intersection point. Is that good? That's basically, there's a shifting of a different perspective into this question here. Sometimes it's a pure math problem, you solve intersections, and then you relate that. Sometimes you relate that to most of the time here relate that to the physical motions, right? Yeah. So with this speed, you will be able to catch. Okay? Yeah. So I'll show you animation at here, just to illustrate this this problem here. Okay. Yeah. This is a MATLAB animation at here. It's a little bit small, but the idea is basically we're going to plot two straight lines, and we're going to also plot the motion for the cat and the mouse based on their speed and initial position. Okay. So as you can see here, this is basically the initial cat trajectory here, and this is the initial mouse trajectory, right? Yeah. So if we don't do any change at all, okay, if you don't do any change at all, okay, so I'm gonna basically comment out all of this here. Okay, if I don't do this, that's basically the first part of the question. We're just trying to ask ourselves whether they're going to catch or not. So this is the idea. See, the blue one is actually the cat, the red one is actually the mouse. Okay, so apparently the motion of the cat is not going to catch the mouse. Okay, yeah. And now what we just did is we find if we keep the initial position but change this velocity, instead of to -3, change that to 6, -9. Basically, how much faster compared to the initial velocity? 3 times, right? So let's see what happens, okay, with that introduction of new speed at here. You see the blue dot, and they catch at the same location, right? Okay, yeah. Okay, so that's an idea here. Now, I want you to think about yourself, okay? So in here, what I did is I changed the cat's speed in order to catch, right? What else can you do? If you keep the initial velocity, not initial, if you keep the original velocity for the cat, but you can also ask the cat to change its initial position, okay? Yeah, a little closer basically, okay? Yeah. So that question basically will be, what will be a proper initial position, okay, in order to catch the mouse? Okay, you can try that yourself. Yes.
So if it moves 3 times faster, then it needs to be 3 times closer if it uses the initial position. So it needs to be a third of the initial position.
Oh, good point. Let me see. What was the original initial position? -4.7, right? No, it's actually. No, initial position, the updated initial position will be 0.1 in order to do the catch. So if you compare 0.1 to -4.7, that's not really right. Well, that's probably a different perspective. But anyway, you can try it. Let's just purely solve it. See if you can get that. All right? Yeah. Any questions? It's all good? Okay, so we'll continue in the next lecture. Okay. Yeah, thanks.